Hey math fans, Alex here, and today we're going to talk about the law of large numbers. So recall that when we proved the de Moivre-Laplace theorem, we defined S sub n as the sum of random variables xi, where all of those were independently and identically distributed as Bernoulli random variables. So they either occurred with probability p, or they didn't occur with probability 1 minus p. So this sum right here was actually a binomial random variable, and if we let a typical element of this random variable be k, k represents the number of successes of your binomial random variable, and if you take k divided by n, we went ahead and called that the relative frequency of success, or you can think of it as the experimental probability. And what we showed in proving the de Moivre-Laplace theorem is one of the assumptions was that k over n, the experimental probability of success, was asymptotic with the theoretical probability of success, p. So we showed it for this very specific case. We showed that the limit as n approached infinity of k over n was equal to p. Another way we could say the same thing, and I'm just going to redefine a couple of variables, instead of taking 1 over n, right, 1 over n times s sub n, let's go ahead and define that as x sub n bar. And sometimes x sub n bar is sometimes called the sample mean. It's called the sample mean because essentially you're taking an arithmetic average of finitely many random variables. Then what you have is that x sub n bar is the relative frequency of success. You have the exact same relation here. Okay, so another way of phrasing this is you could say that the limit as n approaches infinity of xn bar is equal to p. But wait a minute, the probability of success is the same as the expected value of any one of the Bernoulli random variables. Okay, so what we have is that the limit as n approaches infinity of xn bar is equal to the expected value of just any of the random variables. But we only have that if the random variables are, say, Bernoulli. So the question that we want to ask ourselves is it true that the limit as n approaches infinity of the sample mean right here is equal to the expected value of the random variables for other distributions? Okay, so if xi were normal, if xi were Poisson, like does it hold for all of them, or xi may be binomial? Well, the answer is yes, and I'm going to show you a Python simulation to kind of demonstrate this. Okay, so what we have is a really easy program that I wrote, just kind of iterating over the number of trials that you want, and I decided to use the uniform continuous random variable over 0 to 1. Okay, so I commented this out, so let me just show you what it does. We want maybe 10 trials, and it's going to show you 10 random numbers between 0 and 1, and then it essentially averages those together. So the question is, if I could just go back to here really quickly, we want to know, is this average going to be close to the expected value? And remember, the expected value is just smack dab in the middle between 0 and 1. So you would expect 0.5, right? But what we got was something pretty far off from 0.5. We got 0.65. I'm actually a little shocked. Okay, but let's run this again. Let's run it at another 10 trials. This time we get really close to 0.5, 0.483. Let's do it maybe one more time. Okay, and we get 0.583. So 10 trials is measly, right? And I'm sure that if I asked you how to get this closer to 0.5, your gut might tell you to increase the number of trials. And you'd be correct. So let me do, I don't know, let's just jump the gun at 1,000. It's of course going to take a little bit to calculate. Whoops. Okay, maybe I should not print all of these. There we go. So now we're getting even closer to that 0.5. Now, does it have to be close to 0.5? No, but it's probably going to be close to 0.5, especially if I do something like this. Okay, 0.499. Okay, so it holds for the uniform continuous random variable, apparently. So it might hold for all of them, which is essentially going to be the law of large numbers. Okay. So, is it true that the limit of the sample means is equal to just the expected value? Well, let's go ahead and let x sub I be a collection of independently and identically distributed random variables, and in keeping with the notation of the normal distribution, we're going to go ahead and let all the expected values just be mu, and all of the variances just be sigma squared, right? If it's identically distributed, they all have to have the same expected value and variance, so why not call them mu and sigma squared? And then we have that the sample mean is defined as 1 over n times the sum. Okay, so let's roll with this and kind of see what happens here. Okay, so what is the expected value of this random variable? Okay, because if we define a new random variable, we want to find the expected value and the variance of this. Well, the expected value of x sub n bar is just going to be the expected value of 1 over n times the sum, I equals 1 to n of x sub I. Okay, but then we have a situation where this is a constant and it can come out of the expectation operator. So this is going to be 1 over n times the expected value of this sum. Okay, but one of the nice properties about the expected value is that the expectation of a sum is the sum of the expectations. So this is really just going to be equal to 1 over n times the sum from I equals 1 to n of the expected value. Okay, but I said that all the expected values were the same, right? All these were just mu, so I'm adding mu n times. So really this is just going to be n times mu, and 1 over n times n mu is just mu. So the expected value of the sample means, I just showed you that on average, you would expect this quantity, this average, to coincide with the average of all the random variables. Okay, what's the variance? It's going to be a similar calculation for the most part, but there's a catch. So this is still going to be the variance of 1 over n times the sum. Remember, with variance, you can still pull constants out, but you have to square them. Okay, so this still comes out. Just have to make sure to square it. And then you have the variance of the sum. Now you should pause the video and think about the following question. Is the variance of a sum the sum of the variances? So is it true that this is equal to the sum from I equals 1 to n of the variance of x of I? The answer is no. That is definitely not true. Unless, what? What do all the x sub i's need to be in order for me to go ahead and just distribute the sum through the variance operator? They need to be independent. They are independent because they are independently and identically distributed. That's why that's important. Sometimes you can loosen that restriction. This isn't the class for that. Okay, so again, the variance, we define that to be sigma squared. So we have that this is going to equal 1 over n squared times n sigma squared, and that's going to get you sigma squared over n. Okay. So what we have is that for any n random variables that are independently and identically distributed, on average, we expect the sample mean to coincide with the individual means of each of the xi's. Okay, but there's kind of a catch. The catch is that on average, the expected value means that you're essentially taking the average over infinitely many trials, over all possibilities. And we're saying that coincides with the theoretical probability. That's not really impressive. What I want to show that if I take the sample mean, which is finite, I'm taking a finite number of trials, and I compare that to the average of each of the random variables, I want that to be small. Because that means that the sample mean is then going to converge to the population mean. This is called the population mean. Okay? But again, this calculation right here, although it's impressive, does not guarantee that whatsoever. Okay? Now, clearly, these do coincide. At least your gut should be telling you that from the Python simulation, right? If I average all of those results, if I take the sample mean over 100,000 trials, that got pretty close to 0.5, didn't it? Okay, so somewhere we kind of know that these are close, but we need to actually prove this. And the whole idea of the proof relies on the fact that the variance of x sub n bar was equal to sigma squared over n. And since it varied and was proportional to 1 over n, so what we expect is we expect the sample mean to vary less as n gets bigger. So for really large values of n, we expect that to vary less. So that's going to play an important role. And the thing that's going to show us that the sample mean converges with the population mean, that is the law of large numbers. Okay, so let's go ahead and state it as a theorem. Okay, so theorem 6.1 is going to be the weak law of large numbers. And it's basically going to say that xn bar is going to be close to mu. Okay, so we're going to go ahead and let x1 through xn be n independently identically distributed random variables, each with mean mu, variance sigma squared, defining the sample mean as the average of the x sub i's. Then for epsilon and delta, positive arbitrary real numbers, there exists some natural number, like 1, 2, 1,000, this is the number of trials basically, for which the probability that the sample mean differs from the actual mean by less than or equal to epsilon, the probability of that occurring is greater than 1 minus delta. Okay, so in your head, what I want you to think about is I want you to think that epsilon and delta are really, really small numbers that you get to pick. So let's say that you want the sample mean to be super, super close to the actual mean within maybe 0.001. If you want epsilon to be 0.001, fine. And if you want that to happen with probability greater than, say, 0.999, well, then your delta is also going to be 0.001. Okay, so we have two kind of variables that you get to pick, and we're going to kind of show this to be true. Okay? All right, let's prove this. The proof is really nice because we're going to use Chebyshev's inequality. So remember that Chebyshev's inequality was horribly suited for any practical application. Because if you wanted to establish an upper bound, if you wanted to establish an upper bound for a probability of an arbitrary distribution, it was not going to be very good. Remember, I had you do an exercise where you showed that the bound was awful. But what Chebyshev's inequality says is the probability that xn bar minus mu exceeds epsilon, that is bounded below by 1 over epsilon squared times the expected value of xn bar squared. It's just verbatim what Chebyshev's inequality is. So look familiar to you? Okay. Now, this quantity remember that we had that the variance of xn bar, that was equal to sigma squared over n. But the variance of a distribution, by definition, is the expected value of xn bar squared minus the expected value of xn bar quantity squared. Okay, which is equal to the expected value of xn bar squared minus, and then this is just mu. Right, the expected value of xn bar is always going to be mu, so that's going to be mu squared. So we have that the expected value of xn bar squared, just adding this to both sides here, we get that this is equal to sigma squared over n plus mu squared. Okay, so now I can go ahead and plug that in. Let's see what we get. So we have that the probability of xn bar minus mu being greater than epsilon is less than or equal to 1 over epsilon squared times sigma squared over n plus mu squared. Now, I don't want it to be greater than epsilon. I want the opposite. Okay, so look at the theorem. I want to prove that it's less than or equal to epsilon. Well, since that's the complement of this event, what I can do is I can rewrite this as 1 minus the probability of the complement. Those are the same thing. This is xn bar minus mu is now less than or equal to epsilon. That's less than or equal to 1 over epsilon squared times sigma squared over n plus mu squared. Okay? So that's kind of the idea so far. And what we have here is if I want to get this by itself, I'm going to go ahead and subtract 1 from both sides. It actually, you know what, it might be easier just to add this term over and subtract this term over. Okay, so let's do it that way. Okay, so what you're going to have ultimately is that the probability that xn bar minus mu is less than or equal to epsilon, that is going to be greater than or equal to 1 minus this 1 over epsilon squared times sigma squared over n plus mu squared. We're almost done proving the theorem. Because, why are we almost done? We want this, if you look at the theorem, we want that to be greater than 1 minus delta. Okay, so we want kind of, so we want that term plus mu squared. We want that to be greater than 1 minus delta. Because if I give you any delta, I want you to be able to pick an n value so that this holds. Okay? So since I want that to happen, let's go ahead and see if we can solve for n. Well, the first thing I'm going to do is, well, subtract 1 from both sides, and then since I have two negatives, I can go ahead and multiply by the -1. I just have to make sure I flip the inequality symbol. Okay, so really I'm trying to show this. Okay. So then what do we do? Well, let's multiply by epsilon squared. Okay, so then we get sigma squared over n plus mu squared is less than delta epsilon squared. And then I can go ahead and subtract mu squared and then solve for n. I'll kind of let you do that. And what you get in the end is that n is going to be greater than sigma squared over delta epsilon squared minus mu squared. All right? Just manipulating this and solving for n, basically. Now, I can do just a little bit better than that, right? Because you have to imagine, I don't necessarily know what mu is, but if I'm subtracting mu squared from this, that's going to be a bigger number because it's on the denominator. If I'm making this smaller by subtracting mu squared, that is going to be a larger number than if I did not subtract the mu squared. This is delta epsilon squared. Okay? So, the takeaway here is if you want an n such that this holds, such that the theorem says that this is, such that this is greater than 1 minus delta, I showed you that as long as your natural number n, as long as your number of trials exceeds sigma squared over delta epsilon squared, that does the job. So if we go back up to the theorem, delta, epsilon, those were chosen in advance. I didn't really change or manipulate those. But what we did was we showed that there is a value of n based on these constants for which I showed this is greater than this. So we're done. I proved it. Okay. Okay, so what I am going to do is go ahead and summarize a couple of things. Okay, so what we have by the weak law of large numbers is that the probability that the difference between the sample mean and the actual mean is less than or equal to your epsilon, probability of that is greater than 1 minus delta. And this is going to imply let's see. This is going to imply that if I go ahead and multiply both sides by a -1 and then add 1 to both sides, this implies that the 1 minus this probability right here that's going to be less than delta. So I'm going to go ahead and star that. Okay. Now, this is, again, kind of an analysis result because what I showed you in the previous video, the weak law of large numbers, I said that converges in probability. But the form for converging in probability doesn't really look like this. So all I'm going to do is I'm just going to say one can show that star is the same as saying that the limit as n approaches infinity of the probability that xn bar minus mu is less than or equal to epsilon, that is equal to 1. So then what we have is that xn bar converges to mu in probability. Okay, so how can we show this? That's going to be an exercise. It involves kind of the definition of a limit. I don't know or assume that you've seen that before, but it's kind of makes sense, right? Delta is allowed to be as small as I want it to be. Okay, so if you just keep making it smaller and smaller, ultimately this is going to go to 1. It has to be close to 1 so that they cancel each other out, okay, in absolute value. That's what it comes down to. Okay, so let me just summarize. So the summary, if you want xn to be closer to mu, okay, with probability close to 1, increase your sample size. Okay. Now, I'm going to go ahead and stop the video here. In the next video, we're going to kind of explore why this is called the weak law of large numbers. Is there a strong version? And if so, what's wrong with the weak law of large numbers? So I hope to see you there. Hope this video is helpful and have a great rest of your day.